I have prepared this repo with 2 projects that I've already done. So hopefully there will be no hiccups and we can reuse what I already wrote. But we'll try to follow step by step to do the same. So the first project will have, we will write a circuit that will take a magic square 3x3 as public input, and magic square is like it has digits and all the sums of all the rows, columns and diagonals should be equal. So basically we'll prove a knowledge of such magic square 3x3. And yeah, this will be the whole project. And the second project will be more blockchain relevant, I would say. We will prove kind of a test thing that will go in the direction of a Merkle proof. So we will kind of prove a Merkle inclusion against a root. So the root will be public input, and the Merkle path will be a private input. And if we have time, we can also try to deploy this locally on the blockchain and test if this works. This did work when I was doing it. So yeah, I hope people have got the repo. So basically, yeah, you clone the repo. I have it cloned already here. So here in the preparation, I have already done everything, and the workshop itself is intended to be, should be working here. So let's actually start by a setup. Maybe I will open here. So we will be writing this in Noir. Noir is a circuit language developed by the guys who launched Aztec, very cool team. Yeah, so this is the Noir language for writing circuits. And here in the getting started part, basically we need to install it. So let's start with installing Noir. I think, yeah, so I have a link here for the quick start. I have already installed it, but basically what you should do is you should copy this. I mean, hopefully we will not overload the server. But so this is a pretty standard way of installing things, like you install Rust in the same way. So you install Noir up and then you run Noir up. And this will download so this is the language itself, some tools to build stuff and so on. But in principle, you can you use this language to write circuits, and then you can prove the circuits using Barretenberg library. So this is the second step in the setup. Basically, Barretenberg. So here I have installed Noir by using the commands. And here in the here you have the same way of installing Barretenberg. So what we do is by this we install the language tooling, and we install the prover to generate and verify proofs. These are two separate tools. In principle, you can use other proving systems and so on, but this is this is how it should work. So I will give you a moment to make sure you have installed Noir and the proving system, Barretenberg. And yeah, so anybody having some problems? Does it work smoothly?
So is Barretenberg, is it a tool chain on top of a C++ compiler, and Noir is what, going straight to bytecode?
So Noir is a language, Rust-like language that produces circuits, kind of, and in some intermediate representation. And it's written by Aztec team, and the idea of them is that you can take these circuits and plug into different proving systems, kind of backends. And Barretenberg is just one of these backends, as they say. I don't know actually if there are any others for this, but you can kind of prove your circuits with different proving systems.
Also, there's also going to some intermediate form.
Yeah, the circuits will be compiled. So I see some questions. Sorry.
Would you use your syntax highlighter for Noir? That is like legit, because I see there's quite a few VS codes. I'm not sure which one to install.
I don't know.
There should be a plugin, I think.
I have not used anything, but probably they have some. I don't know. Yeah, just install some.
I didn't fully understand. Is Barretenberg just the name of the program, or is it a specific proving system?
So this is a library implementing some proving systems. This is all here in this repo. Actually, they have very good documentation. So this is a optimized elliptic curve library, Plonk prover.
Okay.
Yeah, this is basically a prover that takes some circuits and produces proofs, generates proofs, verifies proofs. No, and the circuits will be produced by Noir. Okay, so I'm assuming that people installed Noir, and let's initialize our first project. So in this workshop directory or whatever you like, let's initialize an empty Nargo project. So Nargo is like cargo from Rust. So we write Nargo new, let's call it Magic Square. And it will create.
Can you make the font size a bit bigger?
Yeah. Let's go. And yeah, so it just created this Magic Square project. So this is an empty project, a kind of initial project that create some hello world type of thing. So this is like a test circuit that they give you. So just a main function that takes two inputs. One of them is public, and it checks that they are different. So what we can do with this is we can build. So let me quickly check the quick start. Yeah, so we can do Nargo check, which will generate a file with inputs. Yeah, so Nargo check will generate this prover.toml file. This is the file that will contain the inputs to our circuits. So I just put some values, and then and then there's also this command Nargo execute. So what this will do is it will basically compile the circuit, run it with these inputs, and produce some artifacts for the basically a compiled version of a circuit. Yeah, so maybe yeah, just one quick thing. So here we check in the circuit itself, we check that these are two different values. So you can see if we put them to be the same, then this execute step fails. And yeah, maybe let's.
If we go a little further, that's sort of basic functionality of the assert. So what is actually happening behind that assert?
So this is this should be compiled to a circuit that takes these inputs, and then at some point it checks that checks the values. I don't know exactly how this kind of assert works on a circuit level, but basically if the check is not correct, so the assert is not correct, then the yeah, I don't know what exactly happens in the circuit, but there is like some indication that this assert has failed.
And the pub and non-pub is a public versus a private input?
Yeah, exactly.
Okay.
Is everyone still with Sergey?
What happens on the low level is usually, I mean, because I've audited some circuits, and so we actually had to like see how it was implemented, and it would basically take the numbers and then bit by bit, it would compare to make sure like all those bits were not like equal, and so they like make a circuit out of what are like called gadgets, because like programming the whole thing top to bottom would just be kind of crazy. So like the gadgets are these little kind of like NAND and NOR gates that you'd see like in a sort of like CPU processing, and so they kind of assemble those together and then make sure that like all the bits in those two numbers didn't match or something like that. It was like that's like the low level tedium.
Okay.
So let's remove the test and clean up the main function. So what we want to do is, yeah, here in the artifacts for the explain. So what we want to check is that we know a magic square, which we will represent by an arrays of length 3. So basically double array. We want to check that it can contain only digits from 0 to 9. We obviously want to check the sums, rows, columns, diagonals, and yeah, we do not insist that numbers should be all different, because otherwise it's too boring. This is a quick link to a Google quantum paper where basically they did something conceptually similar. They proved that they know quantum circuits that possess some specific qualities without, I hope this will not happen. Basically some efficient quantum circuits without revealing them. So this is almost like this, but we're taking a very simple computation with very simple input. So let's see. So in our function, we want to pass the input should be, I suggest you use unsigned integer of length 8. Should be enough for digits. I think this is the correct syntax. Oh no, that's semicolons.
Does Noir have only like fixed size arrays?
I think you can also have defined dynamic somehow, but I don't know if there are some limits. Oh wait.
For most zero proof, everything needs to be fixed size.
Yeah, maybe they have dynamic indexing, but not the dynamic size. Okay. Yeah, I don't know what's happening. So, yeah. So I suggest we write this in functions just for the sake of it. So let's maybe first write a function to check that the numbers are digits, basically. So let's wait, maybe I should just call it square. Maybe that was the problem. So let's define a function, and we do this by, yeah, I think this is the same as in Rust, although I'm not super sure. But so we basically take a function, takes in this the same input, and we want to use asserts to make sure that this all these elements are digits. So this is how I implemented this. Yeah, this is the normal double loop. I think that's how it's written. With the double indices, you can work normally, and something is not working. Yeah, I guess I'm missing semicolon here. Okay.
And what is this square bracket U8 semicolon 3 thing again?
So this is an array of U8. U8 is a type which is an unsigned integer of length 8, and this is the length. It should be
Of 3.
yeah. Maybe this one is missing. Yeah. So I'm
It's
super.
missing return value or something.
Okay, now it compiled. So it's fine without return values here because we just do the asserts. We do not return stuff here yet. But yeah, I was just missing the column here after the. Okay, so actually we can already try to test it with inputs. So here in the prover.toml we have to input the our square. So this is already in prepared. Let's try to now go execute. And just let's try to put something over 10. Yeah.
So you fill in the values yourself here?
So what I did, I copied the input into prover.toml from the preparation. But you can just write it like this. So this is the array of rows. So you can already see that it works. Our circuit already checks that the inputs are digits. So next, what do I check? Or what do I want to check? Maybe, yeah, I was checking the rows, columns, and diagonals. So let's maybe go with this. And we can write function check rows. Again, it should take the as input a square. The same. And it should return. So I return a value here, which I would like to be in this function. I want to check that all the rows have the same sum, and I also want to return the sum so that later we can compare it with the columns. And yeah, also it's an example of how you write a function that returns values. Yeah, so maybe this I will not use. Looks a bit ugly, but so here is a nice feature of Noir language, which they have. And this is called fold, and this is a function that you can apply to each element of the array, and you can do an accumulator. And I think you also pass in a lambda inside, so you can do different things. But basically, you can implement a simple accumulation with this. So let's compare the sum let's compute the sum in the first row. So we would write maybe So we define a variable sum1 equal to 0. Mute means that it's mutable. And or maybe we can already. So we take square 0, which is an array, and we can fold it. And so the first parameter is I think the initial value of the accumulator. Then so it will be 0. And then you can pass the lambda. So basically what happens every time, you take the accumulator and some x, and you return accumulator plus x. And I think that's the syntax. So what it will do, it will iterate over all elements in the array, and it will, so for each element x, it will take the accumulator value, which is the initial one is 0, and it will add the x to the accumulator value. So in this way we compute the sum of the first row. And
does lambda always accept two values, and is accumulator always on the first place?
So this is the for fold function. I think they have more general lambdas, where basically you can.
Okay, it's arbitrary.
Yeah, you can have more general lambdas. So yeah, let's do some 1 in the same way, and so we basically fold the square 1, and just for good practice, let's write some 2 with a for loop as yeah, basically uncivilized people, but you can do it like this. So for again with the loop, so you take sum 2, you have the plus equal, and so again we take the last row and we take the index number I. Yeah, so I think now we have computed these 3 sums, and we just assert that they all are equal. So we assert that sum 0 is equal to sum 1. So the logical operations in Noir are basically bitwise. So you use the single AND, and you have to take the parentheses, because otherwise it will do it in a different order, but basically that's how you do it. We check that they are equal, and I think you don't have a return keyword in Noir, but you just write the variable that you want to return in the end. So I think, yeah, I think that's how you write, and it's not without semicolon. So let's maybe see if it executes. Okay, so I think it's compiling and executing. We can also check how our function works. Check rows. Yeah, so now it works, and maybe we can even test it with the input. So basically we try to check that all the rows are the same. Maybe let's try to have it be not the same, and you see the circuit is failing, and yeah, that means that it actually checks that all rows have the same sum. And we also need to, yeah, we take this return value. We will need it later. Wait, what? Not found in the scope. Oh, yeah. Okay, so I will quickly paste the code for checking columns and checking the diagonals. It's pretty much the same. So we not spend time on this. So this is the function to check that the columns are the same. It works in a similar way. I mean, it computes just by iteration. And again, it checks that the sum of all columns is the same, and it returns the sum of the first column. So we can add it like this as well. And yeah, so this should compile, and inputs. Again, let's modify the square so all the rows are still the same, but columns now become different. So maybe we increase this, decrease this by 1, decrease this by 1, decrease this by 1. So the columns now have different sums, but the rows still have the same sum. And yeah, you see that I think it fails in the correct place. So it works, and yeah, quickly finish with the diagonals. Yeah, I mean, this is not the best code, I guess, and not the most complicated project. And also, I'm not a developer, so I'm probably not the right person to dive deeper into the language. But I'm just showing you how this works conceptually, and you can explore more yourself. Okay, so what I did, now I'm also checking the diagonals, and I also want to check that the sum of rows, the columns and diagonals is the same, kind of nothing crazy here. It's the same logic. So now still compiles, still executes. Yeah, so now what we have is we have written this program that checks that all the numbers are less than 10. So these are digits. The sum in the rows, columns, and diagonals is the same. So we basically have a magic square. And yeah, we have written our circuit. It's compiled now. This is I think this is, I don't know, maybe this is the circuit data, or this is circuit data, I don't know exactly, but one of this. And let's try to actually generate a zero knowledge proof of the program. So this is done by, as I said, Barretenberg library. This is this one. So here you can see how it works with Noir stuff. But basically we need to use this, for example, BB proof. If you installed it, you can check the commands. Yeah, let's maybe just generate a proof. So proof, let's see what we need. So we need this bytecode path. This is the path to a compiled circuit, basically. ACR is an intermediate representation of a circuit that Noir generates. So this is something that we need. I think this is magic square .json. And yeah, and GZ file is actually the witness path. So witness is another name for inputs. So basically this path contains this magic square GZ contains the input to this proof, and as you can see, we have not defined this as public. So this is a private proof, and this the private input, and the private input is basically in this file. So what we need to do is we need to write bb proof, and we say b or bytecode path, and this would be the path to JSON. So it will be target magic square.json. This will be the compile circuit, and we need to specify the witness path. So witness path. This is the path to our input, and this is will be the private input in our case. So it will be the this is the GZ file. So we can also write the verification key. Why not? So this verification keys will be needed for example, for verifying the proof. So we also write it with a proof. So we run this command, and you see something actually happened. So we have proven the circuit, basically. It shows you how much memory it's used. So this one is quite simple program, but you see already 11 megabytes is not nothing. Yeah, but we have written here. You see it generated a proof, generated a file with public inputs. This is empty because we have no public inputs. All the inputs are private. This is a couple of verification key hash needed for verification. So let's check that the proof that we generated is correct. This is done with bb verify. So here the verify needs the proof path. It also needs the verification key path. Yeah, I think you also need the path to public inputs, and maybe we don't need it actually because yeah, let's see. So what we do here is so this is the proof. We pass in the proof, and we pass in the verification key path. So this is something that you use instead of a circuit. This is kind of the extract of circuit information that needed for verification. And this is in VK file. And yeah, you see, proof was verified successfully. Maybe just for the fun of it, what we can do is let's tamper with the proof. Let's change some bytes and see if the proof works. So I just opened it. I don't know. Let's. I have no idea what I'm doing. I just added the file. So now the proof is corrupt. I'm expecting it to be unsuccessful. And you see when I'm trying to verify, something fails, something was wrong, I don't know, but basically we were not able to verify the proof. So this is the, yeah, this is how you can check that something has actually been verified. Yeah, so this is the end actually of the first tutorial. This is very simple, yeah.
Yeah, so the VK artifact is basically the program.
Yeah, the VK it's not a program, it's the part of the program that is needed for the verification part actually. It's like a digest.
If I want to prove something to you, I would give you the program, you create the VK yourself? Or?
Yeah, so exactly. I will basically, in the perfect scenario, we share the program. I generate VK, you generate VK, and I use my generated VK to check that against your proof. But yeah, you can also. So from VK itself, you don't necessarily know what is the program. What is the program? It's kind of hash extracted value. I mean, this VK value already includes actually the private setup, the trusted setup information. It's already baked into VK. So we kind of skipped this step. It was under the hood. But for example, this file with the compiled circuit, it still, I think, doesn't know anything about the trusted setup information. But VK is, so in my slides, I said that the prover and verifier should agree on a program and the proving system. Basically, the circuit, I guess this compiled circuit is the program part, and VK file already contains the information about the proving system itself, the setup, and so on.
Do all ZK systems have like these primitives like VK?
So not all of them explicitly have it, but actually many, I mean, something like VK, every proving system does have. But yeah, I mean, most of them actually do. So this is something that you can see even here in the ZK catalog. You can see basically verifier hashes. So this is it's a smart contract. This is kind of verifier ID. This is the hash of the verification key, which is baked into this verifier. So for example, this one does have verification key. For ZK VMs, it's not so clear, but all the circuit ones, they do have this verification key, and you can see it. Yeah.
And let's say which ZK system produces like the minimum number of site artifacts, like VK, these GZ compiled?
I don't know actually. I have not used too many of them. I think they all produce a fair bit of artifacts. Maybe they. Yeah, I mean, yeah, I think they all should have somehow similar flows. Yeah. So maybe one more thing that I want to show, maybe not really use, but use just yet. But another thing that Barretenberg does is this write solidity verifier, which we maybe will use in the second part if we have time. So this, maybe we can actually do this. So, so this command generates an actual smart contract solidity that you can deploy on chain that that has the verification key baked into it, into the smart contract itself. So what you need to pass is the verification key, which is target verification key, and you need to pass, say the output will be just target, and say verifier.sol. Okay. Yeah, I think it should needs. Yeah, let's maybe do it in the second example. It needs a slightly different compilation, but yeah. So that would be, or this is maybe I can show you what I expected to happen. So basically, this produces this type of smart contract. And you can already see this is a verification key hash baked into this. Here is the verification key itself. Like these are the values written basically from the binary. This is a big file, but it's a smart contract that has a function somewhere below. Yeah, so it has this verify function. And you can then deploy it on chain. But let's maybe at least get started with the second example. So it was nargo new, and let's call it Merkle. So we create a new project from the workshop file. And yeah, so here is my explainer for it. So basically what we would like to do is we will use a simplistic kind of Merkle-like thing. So what we would do is we have an input, let's say we know this value, and we will have a root of a Merkle tree being a public input known to everybody, and we will basically prove the inclusion of a value in this Merkle tree by providing the full Merkle path. And we will say that, so this is just an explainer on what Merkle tree is, but yeah, so we will have a fixed depth of 10 in our Merkle tree, which means that we will need to provide the value and 10 sibling hashes. It will use the Ketchuk hash function, and this hash function we will take from basically we'll take from the library that already exists. So what we would like to do is yeah, so I have some sample values, and
But can we use like simple recursion in Noir?
we can actually. So this, I mean, in Noir, it's a good. You mean recursion in sense of proving and refining, or just?
No, like a factorial function.
Oh yeah. This we can use for sure. Yeah. So we, okay, let's do an argo check, which will create the input file. And so the first thing I want to do is I want to import the library that we need. So this is done in this nargo.toml file that describes the basically dependencies in this way similar to Rust. So here is in the Noir. Let's see. There is this awesome Noir repo, which contains a list of a lot of things, basically links to something already implemented in Noir and so on. So here is a standard library which already implements. So here, for example, we'll be using this one. So there is already a library that implements Ketchuk 256 in Noir. So basically, this is what I defined already in the preparation in nargo.toml. That's how we refer a library. We copy this here in nargo.toml, and we can use then basically this this library. So in our main function, we will have to import I will have to check the syntax. Yes, so this is how we have defined dependency, and then by this line we'll tell to in the dependencies in the package Ketchuk find this function. I think this means that we import a particular function, and then what we can do is this Ketchuk has basically explains how to use it. Maybe let's see how it works. So if you go by this link in Nargo, you can find this function. Yeah, so it compiles. So basically, you see, you can this Kechak function needs input in bytes, and you also specify the length. But then it outputs the byte array itself. I think there is a way to. Wait, did I have it? I think there is a way to print something as well into the console line. Let's see. How do I console print Noir? Yeah, I think we can maybe try to see how it works. Yeah, meanwhile, what we can do is harder than it seems. We can have a look at the yeah, you see it's very easy. Let's try this. Nargo execute. Yeah, okay, probably it's struggling with I don't know. Does it need this? Yeah. So you can see this is the hash, basically. This is how the Kechak function works. It prints you the array already. So this is nice. And basically how I want to use it is in our main function, what I want to do is I want to pass the public root as a public input. Maybe let's just copy it. So this will be the right, the public root of the Merkle tree. Then I want to pass our kind of element as a hash already. So this will be the one that we want to prove the inclusion of. And here are the sibling hashes I want to pass as well. So you see this is array of 10. So each of these elements will be the 32 length array of bytes. U8 is a byte. This is also the format which Kechak function understands. And the sibling hashes will be basically 10 elements. And I have prepared the inputs as well. Yeah. So this is what we will paste here. So these are actual values. This is Kechak 0, I think. Maybe this is the Kechak string 10, and this is Kechak 0, of 1, and so on. And this is the public root that correctly computes from this. But yeah, so this will be our inputs. You see the public root will be a public input, and the rest will be private. Okay, so only we will know it. Yeah, I write one helper function that will compute Merkle root. Maybe we can try to write it step by step. So what I want to do is I want to take my private element, I want to take my sibling hashes, and I want to compute the root, how it should be computed from this. So basically we will take this element, we will take all the provided sibling values, going up the Merkle tree we will compute step by step these intermediate values, we will go to the root, and then we will check that the root that we get from this function is exactly the same as we were provided, the public one. So So this will be the function, and so in hash.
How do you know if you're on the left or right side?
Yeah, this is a simplistic example. I just
Okay,
always
yeah,
assume I'm on
yeah, I just started. I was like, oh man, this is.
Yeah. I mean, this is.
Do you want it for like just say like, okay, we're gonna pretend like we're only on the left side?
Yeah, we're always on the
okay.
left side. Yeah. So here first I define this to be the intermediate hash, and then I will iterate over all sibling hashes. I think the easiest way to iterate is using index. I think it's not there is no nice syntax for dynamic iteration. So I will write it like this.
I mean, this is an arbitrary problem you're solving.
Yep.
Oof, shouldn't use words like that. This is an
No, I mean, this is
arbitrary
absolute.
example that we're reviewing. Sibling hashes actually are private also, the way you've written it. So
Yeah.
it's really two private elements. One
Yes.
is a group of them and one single. I just want to make
Exactly.
sure.
Yeah, exactly.
Okay, but we could also do it with the sibling hashes being,
Well, if they were public though, then you could probably figure out where in the tree you're proving from.
you could, but to get the actual value would be very
Yeah.
difficult. That's the whole idea behind the hash.
Yeah,
this
I mean, you
checking,
could
this
you
is
could have done
arbitrary.
you could have done it like this.
Okay, okay.
Yeah. So I think here we should concatenate. I don't know. So I will define this array, which should be the concatenation of intermediate hash with so there is this nice concat function on arrays, and we should concatenate it with a sibling hash on element I. So we basically go in always our input is to the leftmost. Okay, and then we should set intermediate hash should be the kchuk of kchuk input, and I think like this. Yes. Oh yeah. So this function should also return the root as we computed it. So it should be U832, and yeah. So basically we just recursively concatenate, and let's return intermediate hash, which after the loop should be the root that we computed. So here in this function we let's say computed root to be equal to, basically we call the function private element sibling hashes, and I think I have not found a way to assert that two arrays actually equal, so that's how I do it. Maybe there is a more efficient way. Yeah, that's it. Let's see if nargo check works. Okay, so it compiles, and let's maybe tamper with this value. So now I expect it to fail because the public root is incorrect now, and yeah, something did fail indeed. And if we change it back, then it all compiles. So basically this is a function we just written that takes these inputs. So this private input, these are the sibling hashes, recursively hashes them to a public root, and it all checks out. And let's maybe try to prove this. and see how it works, especially with now with public and private inputs. So yeah, I think we did snargo execute. So we should now, let's see what we have. Yeah, so we have the circuit compiled, and we have this is what is this? This is the witness. So this must be the input to the circuit in some way, in some form. So again, we use BB to prove. What do we need? We need the bytecode of the circuit. So BB prove. I'll write it like this. Bytecode will be and I think this one, and the witness. Wait.
I think it's around.
Yeah. Yeah.
For some reason, the binary is JSON,
Yeah.
which is confusing. But
Exactly. So that's a good catch. Witness should be the wait, and I don't know why it doesn't do this automatically, but maybe there is a reason. Yeah, so you see something happened. What we just did, we generated a proof for knowing pre-image, knowing the Merkle inclusion thing. This example is already a bit more complicated. It consumed, you see, 500 megabytes of memory. And maybe let me first add this thing, and then I will comment on this later. So this actually proves things slightly differently. And yeah, let's maybe verify the proof that it works. So you see we have here the proof. We have public input, so that is not empty anymore. Though there is some data in the public inputs. Yeah, and this actually will be needed later. So we verify. Let's see what it needs. So the proof path will be the proof. The verification key will be the verification key, and we use the public inputs will be public inputs, and yeah, and we do need this Oracle hash. So this thing is needed. Yeah. So you see we have successfully verified the proof. This additional thing is needed to generate the proofs in such a way that they will be a bit more efficient to verify on chain. And yeah, in principle, this circuit can kind of be thought to be a part of an on-chain amp. And here, I think we can try to generate the verifier. So here is we'll try to generate this Solidity file. To generate, we need the verification key. And we need to set the output folder. And wait, what? Yeah, okay. We need to write the file name. Yeah, so from my experience, Noir toolchain is maybe not the best, give you the best explanation for errors. Sometimes you have to figure it out. So basically, we now have smart contract, and this smart contract has this verify function, which in this function you pass the proof that you know basically a preimage, but you also pass the public inputs, which will be the Merkle the Merkle root. And I will not risk copying this, and I will just maybe quickly show you how this should work on blockchain. So basically what I want to do now is I want to deploy this verifier smart contract and quickly check verify a proof on chain. Let's see. Oh, this is not one. So here in the, this is a simple Foundry project. If you know, this is like a toolchain for testing Ethereum related stuff. So now I just launched a local blockchain on my local host. And so what I want to do is I want to deploy the smart contract. This I have written a script to do this. So basically it creates the verifiers. Here I put the smart contract, and to do the deployment, I will just execute this script. Yeah, so this script basically ran and deployed one smart contract, and the address should be so this is the on-chain address of the verifier, and yeah, what we can do is we can just send a transaction to it. So here is our transaction. So this is the address, and we call the function verify, and we just need to fill in the so these are the proof bytes, and this is the public input. So in principle, what you do is you take these values from, I mean, the proof is here. This is a binary. I will not open it. And the public inputs here as well, binary. I will not open it. You have to convert it to a blockchain understandable, basically, format. I have already done this. I think it should be here. So if you're curious, this is how the proof bytes look like. This is quite a lot of bytes. This is a big proof, but it will be manageable.
And the proof is not the program, or it is the program?
No, it's not a program.
Right, okay.
So the program itself already
Supplement.
is, it's encoded in these values. So the verification keys that include basically the program and include the trusted setup information, they all encoded in these cryptographic values. So this smart contract already knows which program it verifies. So let's paste the bytes. And the public input, yeah, is not super optimized. You will see in a moment.
Thank you very much.
Yeah. So this is the public input. It's not, yeah, as I said, it's not very nice in a sense that you see it encodes every value basically as separately, every number from the input. This 1, 55, and so on. I think it should be possible to optimize, but yeah, I just did it like this and paste them here. So let's just try to copy this one gigantic transaction. Oh.
And you can effectively deploy this on mainnet, right? And have
Yeah.
or does it have to be on Nasdaq?
No, you can deploy it. Yeah, like this is Solidity, just Solidity file. So I paste it here.
But actually optimization makes sense because then it's like less gas to
Yeah, so I tried to do it without optimization, and it would just will not deploy because the compiled bytecode was just too big.
But wait, wasn't in the proof, wasn't the Merkle tree like nodes, the leaf nodes, that was a private input?
Yes.
So, but when you verify on chain, like you send this to the chain,
Mm-hmm.
and like the call data is going to be public.
Yes, but so what is in call data? I just pasted the proof.
The proof has got it.
The proof.
Encoded within it.
And the public input, this is the only public input, but this is the root of the Merkle tree.
Oh, that's why. Okay, so that's not each
Yeah.
element of the array is not okay. That's why you're saying it's inefficient because each byte in the Merkle root is stored as 32 bytes.
I mean, I think it should be possible to optimize, but like you can actually see. So here is the input. Like this is 155. This is the public root, like 155, and so on.
Okay,
This is a bit ineffective, but yeah, I mean, it just worked. It succeeded. It was verified. You can. I mean, I will test my terminal once again by maybe modifying the transaction. So this is, let's say we don't know the correct proof. It's off by by 1 byte, by 2 numbers. And let's try to send it and see what happens. Yeah, by the way, I was trying to do this with Remix, and for some reason, like I could not get it to compile and deploy in Remix. I had to do this locally. And you see, there is fail because something failed. The proof did not work. So that's basically how it works. And yeah, this is the end of the workshop. This is what I wanted to
Can you
show.
show one more time the contract? What's in the contract? Was it fast?
Yeah. So this is the contract. This is very cryptic, like you will not be able to understand what's in. But some components, for example, this is the verification keys. And verification keys is the encoded part of the circuit, basically, and the trusted setup. So then this is, okay, this is some helper libraries.
It's not using external libraries, it's all in there.
Yeah, I think this is all self-contained. Library, let's scroll to some interesting part. I mean, this is a huge contract, and verification of one proof costs around 2 million gas with this smart contract. So it's a big one.
But if I had many proofs, would it be possible to create a library out of that? And it's over and over again the same thing, so that I don't have to redeploy all of that stuff every single time?
So this one you have to redeploy every time you change the circuit, just because the circuit is baked into this smart contract.
Oh, okay.
I mean, there are other approaches, and this is, I think this should be.
So if my circuit grows, this contract will also grow?
No, so the size of the, because here you just bake in basically the hash of the verification keys. So you will have always the same size of the contract, but just the content, the cryptographic like hash values will be different.
Okay.
So this, I mean, this is impossible to read. This is unreadable.
Yeah.
This is completely generated, but
Okay, yeah, it's a lot of stuff.
yeah. I mean, what actually is happening on chain, which is maybe a bit more popular, so this kind of simpler verifiers, they have the similar structure. So they also have the verification key kind of hard-coded. They're also very cryptic generated, but they are a bit shorter, I think. So this is, you see this 2,000 lines. This is like 1,300 lines. But still, this is how it looks on chain. This is impossible to understand.
And all like are all of these code generators well audited?
I'm assuming yes.
Because it's like tons of.
Yeah.
This is a risk.
Yeah. So. I think, check out Noir docs. I think they have much more features with what you can do. I think they try to make it very powerful. Like you can do a lot of stuff that you usually cannot do with ZK. Like these types of things are quite nice. Like you can sort your arrays. You have lambdas. Now you have this map function. I actually can do for each with a lambda. Yeah, so they have a lot of stuff that you can do. Like you can normally work with structs and strings, and it's a quite normal language in many ways. Yeah. So that's it. I don't know.
Thank you.